In this video, we're going to look at drawing Lewis structures in which the central atom actually has more than 4 bonds. Consider this first example, phosphorus pentachloride. If we follow all of the steps for drawing Lewis structures normally, we can see something interesting. So let's count electrons first. We know that phosphorus is right below nitrogen, so it has 5 valence electrons. Let's keep a running tally. And chlorine as a halogen, we know that it has 7 valence electrons, and since there are 5 chlorine atoms, 7 times 5 is 35, which means our overall compound is going to have 40 electrons in total. We know that phosphorus is the central atom because it has 3 unpaired valence electrons, while chlorine only has 1. So let's put phosphorus in the center and surround it with 5 peripheral chlorine atoms, which we can then connect to phosphorus with single bonds. Now again, this means that our central phosphorus atom actually has 5 bonds, but we can see how this is excusable when we actually work through this. So, if we count electrons that we've used, 2 electrons per bond times 5 bonds is a total of 10 electrons that we've used so far, meaning that we have 30 electrons remaining. And now let's put all of the lone pairs back on. Let's leave phosphorus's lone pair for a second and just put the lone pairs back onto chlorine. Each chlorine has 2, 4, 6 electrons in their lone pairs, so 3 lone pairs. So that's 6, 12, 18, 24, and if you actually count, that means that we have now added 30 electrons just by putting chlorine's lone pairs on, which means we have no electrons remaining, which means that we're done. Now, one way that we can check if our compound is stable is to calculate the formal charge of phosphorus and of chlorine. So we know that chlorine starts with 7 valence electrons. There are 6 lone pair electrons, 6 non-bonding electrons, and 1 bond that every chlorine has. So since that's 1 electron per bond, now we have 7 minus 6 minus 1. We can see that each chlorine has a formal charge of 0, meaning that it has neither gained nor lost electrons compared to its atomic version, making it stable. Now, if we do the same thing with phosphorus, we know starts with 5 valence electrons. In this case, because phosphorus has no lone pair and only 5 bonds, that's 0 non-bonding electron and 1 electron per bond, which is 5, which means that phosphorus also has a formal charge of 0, which means that it is stable. So how exactly can we justify that phosphorus can make 5 bonds while other elements can't? Well, as we know, as we go from top to bottom on the periodic table, an element's atomic radius increases. And when its atomic radius increases, that means that its valence electrons are farther apart from each other. Now, what that means, if we can actually draw a comparison, because nitrogen has a smaller atomic radius, maybe its valence electrons are here, but since phosphorus is right below nitrogen, which means it has more shells, that its valence electrons are at a higher energy level, maybe its valence shell is actually here. Now, because these electrons are farther away from its nucleus, that makes these electrons easier to lose or easier to separate, which means that theoretically these 2 electrons in the lone pair can be pulled apart and separated more easily. And that's exactly what happens when we talk about the electron configurations. We will explain using electron configurations how this is possible. But because phosphorus's valence electrons are farther away, the attraction to the nucleus is weaker, which means that the electrons in phosphorus's lone pair can now be separated, and these 2 electrons can actually act as unpaired electrons, which means that each of these can make a bond. As a general rule, again, we will look at this in more detail when we look at electron configurations, but as a general rule, after the second period, so after energy level 2, so if n is greater than 2, which simply means that every element after neon can have what we call an expanded valence shell. An expanded valence shell is exactly what phosphorus has here, because its expanded valence shell can make more than 4 bonds. As we see with phosphorus, this is definitely true. Before the next video, there are ample opportunities to practice this. You can actually see that compounds like PCl5 are surprisingly common. We can actually see many examples of compounds that have more than 4 bonds. So before the next video, be sure to try all of these multiple choice and these practice problems here for quick examples of other compounds that can form expanded valence shells.